Hey everyone. Whenever I speak abroad, I like to try and do a little bit to explain where I'm from. I mean, obviously I'm from England. I'm not. Are you? My slides aren't changing. Hang on. Let's see if I can fix this up. It's great to have technical problems straight away. Right. Let's see. Yay, that's good. Okay, so obviously I'm from England, but I'm not from one of the big cities. In fact, the accent that I speak with isn't the accent that I grew up with. And it used to be really difficult to explain to people from outside of England, or even just from the south of England, where I'm actually from. But in the past couple of years, it got a lot easier. For example, I work in London, which is the capital city. It's the one with all the tall buildings. It's the one with the landmarks that you'll recognize. And that's the Google office there in London, Victoria. But that's not where I'm from. I'm actually from right at the other end of the country in a small little town called Carlisle. Now, Carlisle's quite different. It doesn't have any of the big, tall buildings. Large areas of the city are in low resolution. It's actually like that in real life. I don't understand why. But there's not a lot of tech going on, so I had to move out if I wanted a job in tech. But just to drum the point further, this purple line here is Hadrian's Wall, and this was built by the Romans in order to keep out the wildlings, or in this case, the Scottish. So when I moved down to the south, I had to change the way I speak so people could kind of understand what I'm saying. So instead of saying, "Can I have a pint of beer, please?" I would say, "Can I have a pint of beer, please?" And instead of saying, "I'm going to avenge the death of Ned Stark," I would say, "Can I have a pint of beer, please?" So that's me, but we're here to talk about the web, right? And as developers, our responsibilities and our boundaries, they've been changing all the time. And if you think back to the start of the web, it was just text on a screen. And our only ambition here was to have that text be read by someone else. And that was quite difficult because there wasn't really anyone else there. But then we got more and more developers on the web, and we had to compete with them. We had to compete to show that we were better developers. And we did this by putting our pages in space and centering the text and moving things from side to side. We like the moving bits, so we added loads of them. Make it look like there's loads of computer shit going on, because the more complicated it looks, that means the more complicated it was to build, and the better developers we are. We discovered JavaScript at this point, and we used it to create grey dialogues. But then we looked around and we realized that the web had been infiltrated. It had been infiltrated by normal people. And it was like we'd been having this brilliant party for years and years, and then suddenly the parents said, "Oh, we're coming back home now." And we're like, "Oh, we've made a mess of this place. We've got to clean up." So we did, and we cleaned up fast. Usability became a deal. The GIFs, the marquees, that kind of thing, were no longer cool. We started thinking about readability, semantics, accessibility. It was a real back-to-basics move for the web. We got a new browser war at this point as well, with a bigger budget than the previous browser war and more explosions. Netscape reprised its role as Netscape, but it was killed off in the first scene. But some of the new characters were pretty good, the Chromes and the Safaris. A new generation of developers had to care about platform and browser compatibility in a way they didn't before. And we started using JavaScript properly. CSS became a load more powerful. And then our testing surface area exploded. This happened. And this is, we had to care about the user experiences of all these different kinds of device and interaction patterns. And this is where we are now, except GIFs are cool again, as long as they're transcoded from video and they're 3 megabytes in size and they've got a cat in them. But until fairly recently, we'd taken an odd stance when it came to graphical performance. Our goal was usable, not good, just usable. On machines that could draw 3D worlds fast enough to respond to gaming controls in real time, we were happy for our 2D, fairly static pages to perform just a little bit better than unusable. And that's no longer good enough, right? I mean, Facebook did this experiment where they took their mobile app and they artificially decreased the frame rate. It still worked, it was just running a little bit slower in terms of rendering performance. And they saw a significant drop in engagement when they did this. So if you're not caring about rendering performance, your users are going to go to someone who does, if they've got a equivalent product. It was difficult for us to care about graphics performance until the last few years because it just wasn't possible in the browsers. But all the browsers have made a significant leap forward in terms of rendering performance. But we still have to meet them halfway. We still have to put some effort into creating a fluid user experience. And DevTools are here to help us. The timeline that Colt was showing off in Chrome, that it will show you all of the events that are happening in the browser as it's putting the page together. But what are all these steps? What do they mean? How does the browser get from data to pixels? Well, in the beginning, there is nothing. And then the browser is sprayed with HTML text, and it will convert that text into a tree of elements that we call the DOM. And this step, that I'm sure you're all aware, this step is called parsing, and that will show up in the timeline there. You'll see this event as you're loading the page, but also if you send a string to the inner HTML property in JavaScript or outer HTML, something where it has to convert text into a set of elements. We haven't drawn anything yet at this point. At some point, the browser is going to need to know what these elements look like and where they appear on the page. And the first thing it does in terms of doing that is it does a style calculation. And this is where it takes things like the CSS cascade, the style attributes, the font tags, if you're from the 90s, and works out which styles apply to each element individually. And this event shows up in the timeline. There it is, recalculate style. And this will happen when you load a CSS file. You'll get one of these events. Or if you change a style object, if you move things around in the DOM, change a class name, that will cause a style recalculation. Some of these elements didn't get their styles calculated. We can see the paragraph and the div at the bottom there. The reason is that their parent element, that div, that's their parent, they turned out to be displayed none. And so the browser makes a shortcut there because it doesn't care about the styles of those children elements because they have no impact on the rendering of the page. We haven't drawn anything yet, of course, because we need to work out how those styles of each element interact with each other. We need to work out the size and position. We do this by creating another tree, a render tree, full of render objects. And this is where it knows, like, per each thing we're going to draw, what's its size and position, what's its XY coordinate. This process is called layout, and it turns up in the timeline. Mozilla call it reflow, but it's the same thing. So things like changing the DOM, that will cause a layout to happen. Style changes may cause a layout to happen, but if you're just changing something like a background color, that doesn't need to be relayed out again because it doesn't impact the position of things on the page. But even just things like resizing the browser window, that's going to cause a layout. We still haven't drawn anything yet at this point. At some point later, the browser will decide that an area of the screen is showing the wrong thing, and that could just be blank because it hasn't drawn that bit at all. And it will identify a series of render objects, convert that into some drawing instructions, get some pixel data back, and it ships that off to the graphics card and it's displayed to the user. This shows up as paint in the timeline, and it'll tell you not only how long it took, but where the paint was and the kind of size of the paint. Paints are caused by visual changes, which could be triggered by DOM changes, style changes, layout changes, but even just things like highlighting text. I mean, that stuff needs to be painted as well. And that's a lot of stuff for the browser to do, and we know how to measure it, but how fast does it need to be? I mean, we want it to be instant, but how fast is instant? The consensus is within 100 milliseconds of interaction, and this is a fairly old document from 1999. It's the United States Department of Defense Design Criteria Standard, which is fun to say. So you can think of some of these numbers might be lower now because expectations are higher, but 100 milliseconds for an interaction, that still feels about right. So let's look at an example. Here is a page with a lot of paragraphs on it, just like lots of randomly generated ones, loads of them. So what I'm going to do is I'm going to start a timeline recording, and I'm going to resize this box, and I'm going to click this button. Now, when I click this button, all of the paragraphs on the page are going to resize to be the same size as that green box. So here we go. I'm going to click the button now, and then it all changes. I mean, and that didn't feel instant. That took a long time. And we can see this spike in the timeline. And if we take a closer look at that, we can see it's like it's taken a couple of, 1.27 seconds. I mean, there's also this little icon on the side, this warning icon that's showing that something's gone wrong. And if we expand that, we can kind of see what's going on. More warning icons. We see layout, recalculate style happening over and over again. And that's a bad smell. We think something's gone wrong here. The code for that example is really simple. All it's doing is looping through all of the paragraphs and getting the width of the green box and assigning it to the width of each paragraph as it goes through. Now, the first time this code is run, we ask the browser, what is the width of the green box? And the browser's like, well, I know the answer to this. That's easy, because I've just drawn it. So here's your answer. And we assign it to a paragraph. The next time we come round the loop, we ask the browser, what is the width of the green box? And the browser goes, well, that's an interesting question, because I did know what that was a moment ago. But since then, you've been messing around with styles on the page. So I'm no longer sure. So I'm going to have to go and do a calculate style on the layout to check that this answer is going to be correct. And then we get the width of the green box. So in every loop, we have to go through that check. we could do something like this, where we just get the width of the green box once, hold it in a variable, and then go through the loop. It's a little bit more code, but the difference is pretty astounding. I mean, here, I record the timeline, resize the green box, press the button, and things change. And that's the kind of difference we're talking with, just that little change in code. And we can see, things are now just in the 50 millisecond region or whatever. And that's combined recalculate style layout, which only happens once each, and the loop for the click event. If you're going to make changes, especially in a loop, if you're going to be changing styles and reading styles, don't interleave them. Do all your reads before you do your writes, else you end up forcing these synchronous layout operations. And this will result with any property that you read that is style or layout dependent. And there's lots of these, right? And some of them are pretty obvious, things like offset width. Okay, that depends on style information, and offset top. If you were in my session yesterday, we saw that inner text is an odd one. That actually requires style information as well, whereas text content doesn't. And things like scroll positions, etc. Not all CSS styles are created equal either. So we've got a tool in DevTools to kind of deal with this, and it's called continuous page repainting. So if you go to this cog in the bottom corner, in the general section, we've got this option here. And once you enable that, it's going to keep redrawing the page over and over again, and it'll tell you how long it took. So we can see just for this page of paragraphs, it's just a 3.5 milliseconds, not long at all. But if we go in and we add a gradient and a border radius, we've bumped that up. We've added 2 milliseconds to that. So we can conclude from that great, well, this kind of gradient and this kind of border radius are pretty cheap to draw. And then if we add a box shadow, poof, right, we've added quite a few milliseconds on there. We've gone up to 31 milliseconds. But that's still pretty quick. And those shadows are really big as well. The bigger the shadow, the longer it'll take to draw. What about the blur filter? Press the button. There we go. That button feels really slow to press because it takes so long to draw. We're at 340 milliseconds. So blur is like a pretty experimental at the moment. It hasn't really had the performance love that some of the other features have. But if we take continuous painting off and we scroll the document, scrolling is still ultra smooth because that paint operation only needs to happen once. Scrolling is just moving stuff we've already painted up and down, so that's not a problem at all. What about background? So if we enable continuous painting again, we're going to add a background image in. So we can see at the moment we're sort of hovering around the 340 millisecond mark. We add a background in, and there's a little spike at first because it takes longer the first time to draw the background because we've got a resize operation and a decode, well, a decode, then a resize. But then it just returns back to 340. And this is because bitmap images, they're already in the language of the graphics card, so they're really, really cheap to draw. There's little impact there. But something has changed on the page. If we start scrolling now, scrolling performance has just gone completely down the toilet. And if that background isn't actually expensive to draw, why have we lost scrolling performance completely? So to do this, we need to play around with another tool, and that's paint rectangles. And this will show us when and where paint operations are happening on the page. So we enable that here. We get this sort of red outline whenever a draw happens. So as I resize, the whole thing's being redrawn. But as I do things like highlighting, as I said, that's a paint operation, so we can see that happening. But when we scroll, the only thing that's being redrawn is the scroll bar there, and everything else is just moved up and down. So if we enable the background now and start scrolling, we see the red rectangle is over the whole page. It's causing a full page redraw every time. And that's because the background is fixed. It's not moving along with the content. It's staying static in the background. Because if we change that, if we go for a background that scrolls along with the content, our scrolling performance comes back. So you could conclude from that, we should avoid fixed backgrounds because they're a performance problem. They cause too much painting. Well, that's a little bean from the can of Jake's tips, and you're very welcome. But if we take a closer look, the best before date is today. And my partner and I, we have this argument when this happens, because as far as I can tell, she seems to think that as soon as, like, the food will be fine, you can eat the food, but then when midnight strikes on the best before date, it is now poison. You know, if you so much as touch it, your head will fly off, and wasps will come out of your neck or whatever. You know, bad things will happen. But no, it's probably fine. It's just best before that date, and that's what performance advice is like. Browsers develop so fast that when you hear about browser tips, a lot of the things I talk about, they might get fixed during this talk because there's so many commits going on in all the different browsers. So when you hear bits of performance advice, don't just take them for granted. Test them because although they might have been true at the time, they might have gone off. So before you put things into practice, give it a smell first to see what the condition of the tip is. Don't trust performance rules. Use DevTools. Actually see what's going on in your browser today. At the Chrome team, we say tools, not rules, which rhymes, so it must be true, I guess. But developer tools are a great way to find out ways that you might be overworking the browser by accident, or ways that the browser is overworking itself due to some kind of bug, and you might be able to hack around this. So when in Chrome, do as the Chromans do. Use the timeline, use continual painting, you show paint rectangles. We'll come on to composited borders in a bit. But there are tools for other browsers as well, and they're worth checking out. So Firefox has got some great dev tools going on now. It will show you where paints are happening, which is great. Safari's dev tools, I don't like them very much. They have these lots of little tiny hieroglyphic icons. When I click them, I don't know if I'm going to inspect a DOM or open a Stargate. But they have been fixing that, and it's worth checking out the WebKit Nightlies or Safari 7 when that comes out. You can also run this on the command line, and you get an extra menu full of some tools, but that will show you composite borders and kind of roughly where paints are happening as well. And that leaves the browser that everyone loves to hate. What about Internet Explorer? Well, amazingly, Internet Explorer 9 is getting some rendering performance tools. It has a kind of timeline. It won't show you paint rectangles, but it will give you indications of where paints happen. They're actually joining other browsers in this, and it's great to see. I mean, Internet Explorer, it used to be a dick to developers, and we've all been, at the receiving end of that. I don't want to say that, no. Anyway, it's been reborn. The team there are doing great things now, and we shouldn't tar them with past mistakes. But if you struggle to remember which versions of Internet Explorer are dicks, it's pretty simple. It's the versions less than or equal to 8, and that's a nice, easy way to remember it. So look at what other browsers are doing. Look what all the browsers are doing with your page when it comes to rendering, because it might be doing more work than it needs to, either because of something that you're doing that you didn't realize, or a quirk in the browser. What I picked there to show with the background issue, that's a quirk in Chrome and Safari today. It's not an issue in the other browsers. The other browsers have their own issues that don't exist in Chrome. But when you find them, do report bugs. I know it's a pain, and a lot of the bug reporting systems are really terrible. And reporting a bug is not going to solve the problem for the project you're working on now, because you need to ship tomorrow and the browser is not going to have a fix released in time. But it might save your next project, so it's worth doing if you notice a graphical quirk or something like that. What about mobiles? If you think of mobiles as special, in terms of performance, you're probably doing it wrong. You're probably going about it wrong. Mobile is mostly a UX challenge. If you think about mobiles, they've got lack of keyboard access, or some mobiles do, cellular data, battery, it's got touch interaction. But none of these things are unique to mobile. You get these on other devices as well. Mobiles are small, and they can be slower. And that's pretty much it in terms of mobiles and performance. If you're struggling to do something in 100 milliseconds on desktop, you're probably not going to make it on a mobile phone. But there is one difference that I do want to cover. This is the tap delay. So here's a lovely rainbow of colors, and when I click them on here, they change color. And the code for this is really simple. And I'm just looping through all of those divs, assigning them a color of the rainbow, and then on click, I'm just going to switch it to the opposite color in the spectrum. So it's pretty quick there. But if we look at what happens on mobile, it's really, really slow, really slow. And yes, mobiles are slower. They have slower processors than most desktop machines, but they're not this slow. This problem is not caused by rendering hardware. This is caused by an event system. You see, because you can do this, you can pinch zoom to scale pages, but you can also double tap, and that brings a paragraph up to full width. And because we have this double tap gesture, whenever you do a single tap, we have to wait to see if you're going to tap again. We have to wait and see if it's going to be a double tap. And that wait is 300 milliseconds, and that's what you're seeing there. And it's just such a massive performance problem. This is the reason people think the mobile web is slow. It's not because the devices are slow. It's just this 300 milliseconds. We could fix this by adding a touch end listener and go away from the click listener and just pipe straight into the touch event. And that works. And look, that's much faster. There we go. But when we scroll and we stop scrolling, we wouldn't expect that to happen. We wouldn't expect a link to be clicked in that case. Because it's still a touch end, even though you're scrolling. Or that's how it works in some browsers, like iOS, Safari does this, the old Android browser, which is on the screen, and Firefox does this as well. Chrome doesn't. Chrome realizes that if you're doing a scroll, it's not going to fire a touch end. But I think they're actually going to change that and come into line with the rest of the browsers. But the spec is really unclear here. No one's doing it wrong. Microsoft's pointer event spec does make it clear, and this is much better. If a pointer up event, that caters for lots of different interaction types like mouse and pen and touch. And it does say in the spec that if a scrolling or a panning action is instigated, then you wouldn't fire a pointer up because the hardware has taken over that event. So you would only get to hear about it if you, on a pointer down, you would cancel that, and now you were in control of the event stream. But even then, we're only fixing the problem within JavaScript. What about things like links? What about things like checkboxes, and other inputs? They're still affected by the 300 millisecond delay. You can actually get around this with FT fast click. And this is just a script. It's going to listen to touch events, and it's going to look at how far things have moved since the touch event started and ended. And that will decide whether it's going to fire a click event really quickly. And this is at the expense of losing the double tap gesture. But if you're caring about mobile layout, then you don't need that double tap gesture at all. Alternatively, you can go for a fixed viewport. Because if you've got a fixed viewport, you can't zoom in, so double tap is completely redundant. And some browsers will optimize for the situation and remove the 300 milliseconds. And that's Chrome and Firefox. Safari doesn't, because Safari, if you double tap, it'll actually scroll the page a bit, which is a weird gesture, but it means that they are kind of locked into keeping that 300 millisecond delay, even if it's a fixed viewport. But being able to scale the viewport is actually quite a nice accessibility thing as well, or if you just wanted to zoom into an image or something, it's a nice gesture. So people don't really want to fix the viewport. At Chrome, we're looking at fixing this. We're looking at if you set a viewport like this, that we're going to get rid of the double tap gesture unless someone started pinch zooming in, because normally your paragraphs should be readable. So we're going to look at ways we can safely remove this without breaking user expectation. In the meantime, the FT script is probably your best bet. So 100 milliseconds feels kind of instant. Anything over that, not so much. But what about this? This is some snow animating. Each frame comes in with a 100 millisecond delay from the previous one. And here's a touch action where that box is moving. It's changing position every 100 milliseconds. 100 milliseconds is not good enough for animation. It's not good enough for continual tactile feedback. We see our apps performing like this. We must ask what the frames per second is going on here. And in that case, it was 10 frames per second. And that's not good enough. So if that's not good enough, what is? And this is when I get to nerd out about frame rates a bit. So back when Cinema with Audio was introduced, everyone sort of agreed on the frame rate things should be played at. And a standard emerged that frames should be 42 milliseconds apart, and that produces 24 frames per second. Film being a series of stills, and a light is shone through them to create the picture on the screen. And film was expensive. So 24 was picked, not because it's great, but just because anything lower was unwatchable. 24 isn't good, it's just one higher than unwatchable. And things stayed like that for 90 years, and The Hobbit being the first mainstream film to change that and went up to 48 frames per second. But meanwhile, this was happening. People were getting color televisions in their home. I love this advert, like it's living color, blah, blah, blah. It's like having two sets in one. And if you read the rest of this advert, their justification for why it's like two sets in one is because not only can it display color, it can also display black and white. And if only we could market progressive enhancement like that. It's like it works with JavaScript, without JavaScript. You're getting two sites for the price of one. It's great. The picture in a CRT TV is created using an electron gun, which sounds really sci-fi, and it looks really sci-fi. It's an incredible looking thing. And that beams the picture. It starts from the top, and it scans from top to bottom. And it does that 60 times a second in the US. In most of the rest of the world, it does it 50 times a second. And the reason for that is that's the power supply frequency. And it was cheaper to make TVs if you could use the power frequency as the clock. So you didn't have to have something else handling that. So that's your maximum frame rate, 50 or 60, depending on the country. Although some high-budget TV shows, they tend to half that. They'll skip every other frame in order to look more like a film, to be closer to a film's frame rate. And that's why The Hobbit, to people, looked like a cheap soap opera, because it was closer to what they perceived to be a cheap TV refresh rate rather than a film. Computer monitors could be driven at different refresh rates, and it was better to have a higher refresh rate because it was easier on the eyes. You didn't see the flicker as much. So we tended to run them at 75, maybe 100, 120 in some cases. But we don't use CRTs anymore. We use TFT or plasma screens. Not as good for cats to sit on top of, but better for our eyes. And the refresh rate, having a higher refresh rate, isn't really a benefit here because you don't get the flickering thing. So things kind of average down on 60 hertz, and that's kind of what we all use. So you'll encounter the odd projector that wants to be at 75, and some laptops will go down to 50 when they're on battery power, but 60 is the most common. If we want to deliver smooth motion, then we need to, this is what we should be aiming for, to deliver a new frame for every refresh of the screen. And when we're talking about 60 hertz, that gives us 16.67 milliseconds to do everything we need to do and get the new frame on the screen. And that's not a long time to edit the DOM, calculate styles, layout, and paint. And if you're on a mobile, there's a lot, that deadline seems even shorter because it's a lower powered device. However, most instances of animation on the web, they're shooting themselves in the foot. They're not starting their work early enough, or they're making the browser do more work than it needs to. So imagine these are our refreshes, each of them 16.67 milliseconds long. And imagine our frame takes 10 milliseconds to construct. There it is. So we do that work, and that will appear on the screen in the next refresh, and that's great. But when should we start getting the next frame together? We could start our work straight away. We could code that. We use set timeout 0, and that looks like this, and those frames are appearing on the screen. However, a number of those frames that we create were never made it onto the screen. Because we were creating too many of them, they never had the opportunity to appear. And by doing that, we're going to be using too much CPU as well, and that means battery usage on devices with battery. And at some point as well, another browser tab or another application is going to be scheduled in to use the CPU, and you're hogging it at the moment. So you'll be paused for this other application to do its thing, and that's the point you'll start dropping frames. We could go for a set timeout 16.667, and this is pretty much what jQuery does for its animation. This looks like this, and that works for the first 4 frames, but we're starting our work later and later into the refresh. And this is because set timeout doesn't guarantee when the function will be called. It only guarantees it's going to be called after the number you give it, and it's rounded into a fairly inaccurate internal timer. So by the time we get to this 5th frame, we've missed our deadline. We're kind of halfway into the next refresh, so that frame is going to be displayed in the refresh after, and we've dropped a frame. But that's still 58 frames per second, right? It's not too bad. Who here prefers orange juice to have bits of orange in? And who prefers orange juice to be smooth? Yeah, I'm with the majority on this one. Some people have no opinion on orange juice, I could see from that, but that's okay. I used to work with a guy who said, no, I really like an orange juice that I can chew. He's going to be delighted when he discovers oranges. That will be his favorite thing. But imagine you're drinking a glass of milk, and as you drink it, a lumpy bit goes into your mouth. Not pleasant, not nice. Wasn't expected. Well, that's what animation is like. Animation is like smooth orange juice, milk, and farts. Lumps are unexpected and unpleasant, and we don't want them. So if you have a look at this animation and study some of the bigger bits of snow as they fall down the screen, this is running at 30 frames per second, which is half of the refresh rate. Compare it to this, which is running things the more jQuery way. This is using set interval. If you see, it's kind of, every little bit is, I hope you can see it on the projector, but every bit of snow is kind of juddering as it goes down, as it's skipping frames. It's a higher frame rate overall, but the experience is worse. It's juddery, it's lumpy fart milk animation. We don't want this on the web. And this is because 58 does not divide evenly into 60. The highest possible frame rate is less important than having a consistent frame rate and in sync with the refresh rate of the screen. It's already been mentioned today, but the answer to this problem is to use request animation frame, but this is why it works. It will schedule your JavaScript to be called at the start of a refresh. It gives you the maximum amount of time to get your frame ready for the next refresh. And when we do that, and hopefully you can see a difference. If not, you definitely can on a laptop screen. This is running at 60 frames per second without dropping any frames at all. Support for request animation frame is pretty good. All of the browsers have had it for a while, and you can polyfill it as well for older browsers. And newer older browsers, things like the old Android browser. It's a really simple polyfill. You fall back to set timeout. As long as you use date.now as your timer, that will work. As I said, jQuery doesn't do this. It does things the old, lumpy, horrible way. But if you include this plugin in this really tiny plugin, which you will just roll into your jQuery file, it will fix it to use request animation frame. But why doesn't jQuery just do this? Why don't they do this by default? And it's because people have written code like this. So here we've got a carousel, and then every 5 seconds using set interval, we're going to move to the next carousel item, and that's going to start an animation. Now, set interval will continue to run even when you're in a different tab, or the browser's minimized, or you're somewhere else, whereas request animation frame says in the spec, and this is what the browsers do, they will pause the animation while it's not visible. And that's great, because that saves on CPU. But because these two things are operating in a different way, the user goes to a different tab, and every 5 seconds, we're calling next carousel item, but those animations aren't running, and then the user returns to the tab, 10 animations try and happen at once, and the world explodes, or whatever happens. Some kind of bug happens on a page. So don't write code like this. Instead, if you're calling animations on an interval, don't queue up the next one until the previous one is finished. And that means your animations can pause, and everything will just work out fine. This idea of synchronizing frames isn't particularly new. I mean, we've had this problem in films and TV. So in the US, the screens are at 60 hertz, or modern laptops and computers running at 60 hertz. But we want to watch films on those screens. And films are at 24 frames per second. And that doesn't divide into 60. And in modern dramatic TV shows, they're all at 24 frames per second, like Game of Thrones that we saw earlier and Walking Dead. They're all at 24 frames per second because they want to look like a film. It doesn't divide into 60. The solution to this was to do this, which is a 3x2 pull-down, whereas the odd-numbered frames are shown for 3 refreshes and the even-numbered frames are shown for 2 refreshes. And this means that the odd-numbered frames are on screen 50% longer than the even ones. And this is noticeable. So next time you're watching a film on your laptop, watch out for the smooth pans across the countryside or whatever. The motion is terrible. It's really juddery. And I might have just spoiled watching films on your laptop for you. But your TV might be doing the same. I mean, most modern TVs will support 24 hertz, but not all of them do. But even then, the device that's connected to the TV might not be telling the TV to go into the correct mode. And Netflix on the PS3 is an offender here. So you're watching, even with a TV that can do 24 frames per second, 24 hertz natively, it's going to keep it in 60 hertz, and you'll get this juddery motion. We had a similar problem in the rest of the world, in the UK. We had 50 hertz screens, and we wanted to watch films there. 24 doesn't divide into 50. But it almost does. Almost does. Ghostbusters 2 is 5 minutes shorter in the UK than the US. Not because you've got extra scenes, we just play the film a bit quicker. Go from 24 to 25 frames per second, that divides fine. Everyone speaks 3/4 of a semitone higher, but you don't really notice it, kind of, maybe. Sometimes they resample the audio, but it tends to be higher quality if you just pitch up. So what we've been talking about so far is software rendering, but the biggest... I'm really nervous about this slide because this crashed on me this morning. I'm spinning up a virtual machine because I want to show the difference between how Internet Explorer 6 renders stuff and how other browsers... I think it's fine. OK. Yeah, so most of what we've been talking about so far is software rendering, but one of the biggest changes we've had so far is... Oh! I don't really have time for... OK, hang on. I might skip a demo. OK, I'll just talk about it. Don't worry. Let's get that out. OK. Oh, I'm just kidding. Of course I'm kidding. But this is a great example of the difference between hardware and software rendering. We take something like Windows XP, the screen is a single canvas where the operating system knows what every pixel is and nothing more. So if we wanted to move a window, say this window, you click and drag, it would pick up those instructions, it would take these pixels and it would just copy them into the new location, because that's a really fast operation. But then the operating system identifies areas of the screen that are now showing the wrong thing. And it sends messages to the applications that are now in charge of those pixels to say, you need to redraw this area of the screen. In the top right-hand corner there, the control panel is underneath, so it sent a message, and it responds, and it redraws. However, in the other two boxes, the application underneath is Internet Explorer, so it gets sent a message saying you need to redraw. But Internet Explorer has crashed, so it can't respond to those messages, and that's how you can paint the window around, and it doesn't update those pixels. It's a single canvas updated by the CPU pixel by pixel. That changed in Windows Vista, and it had already changed in OS X and some Linux Windows managers as well. The desktop isn't a single flat canvas, but rather a whole series of canvases that are all sort of stored on the GPU. It knows the entire pixel content of each window. And in this model, moving a window is really, really cheap, because the CPU just says, hey, graphics card, that thing you know about, move it over here. And it can respond, and then it can composite everything together and produce the picture you have. So even if an application crashes in Vista and most modern operating systems, you can drag the windows around and you don't get that painting effect. If you work in Photoshop, software rendering is like a flattened image. If you want to move something around, you will have to manually repaint what was there before. Hardware compositing is more like a multi-layered PSD, where you can just drag and move stuff around because you already know the pixels underneath. The web used to be this flat canvas, but more and more is moving to the GPU, which is great, because it turns out the graphics processing unit pretty good at processing graphics. We just haven't been using it for so long. So when the browser knows about all of the stuff it's going to render, identifies particular elements in the tree and their children that deserve to be drawn separately on their own layer, and then composite it together to form the whole picture. And that event shows up in the timeline as well. So here we're seeing 2 paints, and then composite layers there as well. And that brings everything together. So the first 2 steps there, that's where the individual images were created. Composite layers brings them all together. You can tell which elements have GPU layers. In the DevTools, there is a Show Composited Layer Borders option there. And that'll draw an orange box around everything that's got its own layer on the GPU. Let's look at an example. I call this Snakes on a Geometric Plane. I like to pause for an applause at that joke, but never mind. First things first. Oh, thank you. Yeah, it is. What the frames per second is going on here, because it's really, really slow. And if we look at the DevTools, we can see these huge paint operations. This is running very much like Windows Vista. Windows XP. It's being full redraws every time, one flat canvas. The code for it's pretty simple. We're animating top and left using CSS. There's no JavaScript involved. But if we added translate Z to each of those blobs, the animation goes from this to this, like massive speed up. And that's just putting each of those blobs onto the GPU. The timeline agrees as well. Our cost is now in recalculate style and layout, and the paint cost is really minimal. In fact, those paints are a bug. We're fixing that. But the frame rate's still not great. We're hitting 30 rather than 60, but we can fix that as well. Oh, the fact that Translate Z is going to put this stuff on the GPU is definitely a jake tip. That might expire, but it's been like that for a while, and it's something you can kind of rely on. If we change the animation from top and left, and we switched it to using transform, the browser can make another optimization, and we go from this to this. And I don't know if you can see the difference from where you're sitting, but the timeline will show us we are now hitting 60 frames per second. In fact, moving those 300 objects around is taking like 2 milliseconds. It's gone from being quite a heavy operation to being nothing at all, because it's now in something that the graphics card can just instantly deal with. And this happens on mobile as well. We're going from left to the right by using like a transform-based animation. Animating transforms gives us another advantage as well. On the left, we're animating using top and left. On the right, we're animating using transform. And we can see the one that uses transform can glide smoothly between pixels, whereas the one that is using top and left can't. Most browsers do this. Firefox is a little bit trickier. In fact, Firefox will still kind of snap between pixels with a translate-based animation. But for some reason, and this is a policy that they've deliberately done, and it doesn't look like they're going to change their mind, which I think is a bit of a shame. But you can hack around it by adding a very, very small rotate. And if you do that, suddenly you get smooth animation. So that triggers the hardware stuff. So these layer things, they seem like the magic bullet to rendering performance. But if we take what we had before and we take off the shadow and take off some of the other stuff and start changing the colors every couple of seconds, that's working well. And this is using Translate Z. But if we look on mobile, when those colors change, we get this awful jank. It kind of pauses, it does that. And if we look at as soon as we remove Translate Z, like we go to the old way of painting, it goes to what we're seeing on the right here. It's actually much, much smoother. What the frames per second is going on here. If we look at the remote DevTools, we can see that when those colors change, it gets hit by this ton of paint operations to change the color of all of those blobs. Even though it's kind of going to produce the same output, it doesn't know that in advance, and it's going to do that 80 times. And when we take Translate Z off, we're still not hitting a great frame rate, but it's a consistent frame rate, so to our eyes, it looks much better. I'm going to rocket through the next few slides. We've seen the benefits of layering, and we've seen that you can cause problems on mobile with extra paints when you've got layers. But there are other issues just by having too many layers as well. This is the Guardian website. It runs at 60 frames per second. This is a 30 frames per second capture, so it is actually better than it looks. And we can confirm that using the frames per second monitor in DevTools. We're not using a lot of GPU memory. We're hitting 60 frames per second. But if I made everything on the page have its own GPU layer by using Translate Z0, now, I'm going to start scrolling the page, and when I hit 0 on the keyboard, it's going to make everything a layer. So everything is going fine, hit 0, and then scrolling performance just absolutely dies. And because this is a 30 frames per second capture, it's making it look not as bad as it actually is. But if we see we've gone down to like 25 frames per second, and we can see the cause. We're hitting up against the GPU memory, and that's when swapping happens, and that's when we start dropping frames. Forcing something onto a layer is like drinking a cheap beer. There are some things that I'm better at after drinking a beer, like talking to people and playing pool and things for some reason I get better at. But even though I get better after one, like if I drink a lot more, then things start to go downhill, and I get worse than even without any beer at all. Like start to slur or whatever. I went home for Christmas, and I was staying at my dad's place. I was staying in my old bedroom, but he turned it into his study now. But there was still a bed in there. And I went out with school friends, and I got drunk in a way that you only get drunk with old school friends. I made it back home fine. Everything was okay. But then in the middle of the night, I woke up, and I was standing up, which is not normally how I sleep, and I was over at the other end of the room. And the bit of my brain that's in charge while I'm asleep, the Night's Watch, I think it's called, but it gave me an update onto the situation. And it's like, Jake, here you go. So, you've been sick in your dad's drawer. So if you'd like to deal with that, and then we can get back to sleeping because we're very, very tired. And I felt like I was gifted this situation that I hadn't created. It was like the worst episode of Quantum Leap ever, and I had to just deal with this. But that's what using layers is like. Layers like a beer, and your desktop can hold its liquor, whereas your mobile phone with less memory, if you give it too many of these, it's going to be pulling chunks of stick out of a stapler at 4 o'clock in the morning, trying to repair the damage it's done. There are no magic rules around layering, none that will stand the test of time, so test a particular situation. But just to sort of wrap up, here are the situations that create layers in Chrome and Safari at the moment. If you have a 3D transform, it gets a GPU layer. If you're animating or transitioning transform opacity or filters, it gets a GPU layer. Flash Silverlight, that'll happen there. Canvas, video. Fixed position elements really benefit from being on the GPU, but we lose subpixel font rendering, or like the clear type font rendering. So that will happen on a Retina Mac, but not on other devices. We're working on fixing that. And soon we'll fix that background issue by doing this, and that's what's in the Nightlies at the moment, and the WebKit Nightlies. All of these, definitely Jake's tips. These things will change. Use composited layer borders. That will show you what's actually happening in the browser. The one thing that you want to watch out for that is always going to be the case is anything that if you've got an element that's sort of definitely a layer because it's a video or whatever, and you have an element that overlaps it and appears on top, that will become a layer. And that kind of makes that's common sense, right? You can't layer something on top of something without it being a layer itself. But that catches people out, that you end up with things like that happening when you don't expect. And we can see that happening here. So I've got this green box here. I'm going to show composited layer borders. And as I move that green box down behind these paragraphs, we will see them go on and off the GPU. So that scrolls down. There we go. They're getting that yellow border. And when the intersection stops, they drop off the GPU. And that's not without a visual impact as well. Like I say, we have this font rendering pattern like most LCD screens, most operating systems use, where you can see this color fringing to do the subpixel rendering. But we can't do that on the GPU layer because it's more complicated than a simple composite. So we can see when that box intersects, it drops down to simple anti-aliasing. So if you've got an item that you know is going to go on the GPU, if you can bring it with a Z-index to the top of the stack, that will prevent other things accidentally becoming part of getting their own GPU layer as well. So that was a lot of stuff to fit into, well, a slightly overrunning talk, 42 minutes. But what I'm trying to say is, yeah, always ask what the frames per second is going on, because this really matters to users. And even on a subconscious level, they will go to apps that seem to be running smoother. And you do this by don't overdo layout, avoid like the layout thrashing stuff. Be mindful of painting costs. Use the continuous paint mode. See how much time it's actually doing to render that background. Could you recreate that effect with something simpler, like a bitmap, for instance? Don't make users suffer this 300 millisecond delay. And this is something really that all the mobile browsers need to fix, but in the meantime, you can work around it. And the speed increase, how faster the web feels when you remove this, is amazing. And use one of the animation methods that will synchronize to the refresh rate of the screen. So that's CSS animations and then request animation frame if you need to drive it yourself. And also, the GPU, if there's something that you're part of the hardware that most web developers are pretty unfamiliar with, that they need to be familiar with, is how the GPU works. And it's so important to kind of learn how that all comes together. And with that, I would like to say thank you very much, guys. Cheers.